This video, which is lesson number 4 of 13, is going to talk all about contours, making contours using QGIS specifically. A later lesson will get into making contours using Kartoppelauten. This lesson is going to be using QGIS, as well as creating other products that are quite good for making maps. So earlier we talked about coordinate reference systems, and I encourage you in Western Washington to use EPSG code 26910, which is a UTM based coordinate reference system, and use this for all your projects. If you're in Eastern Washington, you might start using 11 North, and it might be 12 based on where you're at further in the United States and so on around the globe, but UTM is a good system. UTM describes really just the X and Y axis and not really the elevation, and it describes it on a perfect sphere. But it's a well-documented method of describing position using UTM, and everybody understands this, so that's why it's really good. And it's not the same as lat long or MGRS. It's slightly different, and it's really good to learn how to use that, even if you haven't learned it before. You might be an experienced orienteer who has no idea how to use UTM coordinates and find yourself in a situation where you're lost and you have access to your iPhone, which can spit out a UTM coordinate, maybe even a lat long. Either one of those things would be really useful if you were lost and had to transcribe or tell somebody where you were. So basically we're going to use UTM for our project, and we're going to use the EPSG code 26910. Recommend seeing the previous video if you're not too sure about why. Alright, so we're going to talk initially about getting contours into QGIS. We're also going to talk about other base map things as well in this video. So the first term I want to go over so you understand is the DEM, or Digital Elevation Model. I'll call this the DEM throughout this video and probably speak to it flippantly as if you understand what it is. But a DEM is really nothing more than a way to describe the shape of the Earth. And there's sort of two de facto type of DEMs that are created whenever they create these. One is called the Digital Terrain Model, and sometimes called the Ground Model, Digital Ground Model. And this model describes what the Earth would look like without the trees and buildings and just the bare Earth. Sometimes you'll even see it written as bare Earth. There's also the Digital Surface Model. This is used for vegetation and roofs and things like that. So it'll show what the Earth looks like, including all the things on top of the Earth. So it would be what the Earth would look like if you basically draped a big blanket over the top of everything, and what shape would that create. So those two things are important to distinguish. We always use the digital terrain model when creating contours. That's very important. This is why orthography, or using photographs or photogrammetry, does not create good contours where there is a lot of vegetation, because the contours are interfered with by the things on the surface. The digital surface model, however, is very useful whenever you're trying to show the items on top of the ground, and I'll show you some examples of that and how I use it later on. And you could use your own imagination, of course, to come up with creative ways to use that. I like to get them both, and in all honesty, Kartoppelauten uses both too. However, Kartoppelauten uses something called LiDAR, and LiDAR is slightly different than a digital elevation model. Digital elevation models are created, and they create a perfect grid of squares that cover an area, typically very small in size. The smaller it is, the more detailed it is. But the digital elevation model is a perfect grid of squares where each square contains an elevation value. LiDAR, however, is a laser that is shining across the Earth, spitting out millions and millions of light pulses. And as those light pulses hit the ground and bounce back up, we can determine a few things from that light pulse. Basically, the main thing we're determining, though, is the elevation of the ground, and we do that by determining how long it takes to get from the airplane that has a LiDAR sensor, hit the ground, bounce back up, and then be detected. That distance equates exactly to a height difference, which we then store as a latitude, longitude, plus an elevation data. There's also embedded in the LiDAR stream is multiple pulses go out for each LiDAR emission, and how the pulses bounce back and the way they bounce back gets a special label attached to them, and the system that collects the data can determine whether or not it bounced off the ground, off vegetation, and all of that data is stored in the actual LiDAR data field. As you can imagine, there are millions and millions of pulses that get recorded, and so the data is very, very big, and it takes a lot of time to deal with LiDAR. Typically, the LiDAR data nowadays is what actually is used to create a digital elevation model, and they do that by taking this sort of random point cloud, they call it, and then interpolating values into each one of the perfectly gridded square whenever there is not a perfectly gridded square to choose from. So that's what a digital elevation model and its two different main types are and how LiDAR is used. So, previous lesson we talked about gathering data. I showed you some places to get data like road, waters, features, terrain, boundaries, and some places to get that data. Hopefully you went ahead and did that. Specifically, we're going to need you to get the digital elevation model, a digital elevation model of some kind for the terrain and the ground for whatever location you're practicing with, and need you to get the LiDAR data for that, which will come in the .laz file format. Now there's three ways to create contours I'm going to discuss in these lessons, and there's actually more ways than that to create them, of course, but there is the manual method, which is method 1, which is the ideal and best method if you have plenty of time and patience. And that method is you use existing contour data and then you hand draw in the contours on top of it. And the reason why this is better is because it allows the human to get rid of the nonsensical portions of the contours that you really don't need. Often contours get a little bit unsmooth and look a little bit unnecessarily complicated to the human eye, and a experienced orienteer could go through and draw them, smooth them out, and then highlight and exaggerate the places where it's worth exaggerating. So that's really the best way of doing that, but you still need some sort of starting contour to do that. So you can make the starting contour from Kartoppelauten or from QGIS. Kartoppelauten is great because it's pretty easy to do once you understand all of the computer coding that goes into it, and the lines typically do look a little bit smoother than I've been successful at making in QGIS. Not a lot, but a little bit. But the real disadvantage to Kartoppelauten, as you'll see, is that it is very difficult to understand, one, how to set the interval and all the underlying settings, and it's very prone to error unless you have a lot of experience, and it does require you to be computer proficient. Typically you have to have a little bit of command line experience, and there really is no documentation to speak of besides some tribal knowledge on the internet. The documentation that does exist from the inventor of it is English as a second language, so it's difficult to translate complicated ideas into actions whenever that is going on. And I also have had difficulty figuring out how to take tiles of contour data when they expand over multiple areas and then join them into a single smooth contour. I do know there is a command line for this, which I have not had success using. So Kartoppelauten is basically more difficult. QGIS, on the other hand, has a lot more steps. Its advantage is that it's very easy to understand because you do each change to the data in one step at a time, and you see what's going on one bit at a time. And you can manipulate the data as you see fit. You can clean stuff up as you see fit. But the contours themselves typically aren't quite as good as Kartoppelauten, even with a lot of work. But they're close enough that most runners would never even say anything about it. So you'll see that as we build our contours. So the method of building contours in QGIS is you need to get a digital elevation model, and you need to get that digital ground model. Then you need to insert that digital elevation model in QGIS. We're going to clip it down so we don't have to process everything. We're going to create a 1.25 meter base contour, and then we're going to, out of that 1.25 meter contour, we're going to interpolate 2.5 meters and 5 meters. And then we're going to clean and smooth it, save it, export it to OpenMapper, and then we're going to label it appropriately in OpenMapper, which we'll do that in another lesson. All right, let's get going. So So get your dim. Okay, I've already explained some places you can get that, and this is going to eat up a lot of your space. So hopefully you're up with me on this one. You can get it at the Puget Sound LiDAR Consortium data portal or King County GIS portal, other places perhaps. Right now I want you to get all the .las files, the digital terrain model and digital surface models right now. The next step is you need to download QGIS and install these two plugins, which we've done in a previous video. The plugins are Quick Web Map and Generalizer. And once you've done that, we can drag our dim onto our canvas. So here's our canvas in QGIS. And what I want to do is kind of start with a blank look so that you can all be on the same page as me. You will have a giant canvas here, and you might have something on the left-hand side that you can close out. But we'll turn it on through the view setting. View at the very bottom has some things you can turn on. And the first thing I want to turn on is the layers themselves. It'll show you all the different layers that exist. The second thing I want to go in the view menu and turn on is the layer styling. So now we can style things as we go. I have nothing turned on right now. I do have some data that I've got from a previous lesson stored on the side over here, which it looks like this, but we'll get to that later. But the first thing we are going to do is we are going to find our raw data, and we saved ourselves the digital surface model called the bare earth. We've saved that, and we're going to drag and drop the .tiff bare earth BE into the canvas. And it should look something like this. You'll also see some elevation listed here in the different colors. So it's saying that minus 39.94 feet is black and white is 1197.69 feet. That's the extent of the high and low area. And we're going to take a subset of that digital surface model and only clip off some of that so we don't have to process contours for this entire area, which would be huge. So we're going to find the area we want. The best way to find the area is use one of these quick map service plugins that I mentioned earlier. Web, quick map services, Openstreetmap is what I always use. So I select an Openstreetmap plugin, and let's just bring it out to itself here. Okay. This is the area I want around St. Edward's Park, so I'm zoomed in. Let me just adjust it exactly how I want it. Alright, so I'm zoomed into that area right there. It covers the top edge and the bottom edge of the park, and then a bunch of stuff to the right. I'll go ahead and turn that off. Now I'm going to save just this area. I'm going to save this exact same picture, but just a clipped version. And I'm going to do that by right-clicking on it. When I right-click on the layer, I get a feature that says export. I say save as, and I say map canvas extent. Very important. That makes sure that if you say the layer, it'll give you the entire layer that you have selected. If you say map canvas extent, it'll just give you what's in the window at the time. We're going to save this as a GeoTIFF. The file name, we are going to go to our training map folder where we have the raw data and the EPSG 910, and we're going to save this into the raw data format, and we're going to say clipped DSM, and we're going to not change the coordinate reference system at this time. So we're going to use 100026, and we're going to save it as that. And it'll take a minute once I press the OK button, but you'll see the bar at the bottom working. And once it's complete, you'll get a layer exported alert, and you will see a new file into the window. So now we have two files. You see the original and the clip section. We don't need this original anymore. So we can right click on it and say remove layer. We don't want to mess with extra data if we don't have to. So now we're just messing with this clipped DSM for all of our stuff going forward. And this is where things get pretty easy to make contours in QGIS. This raster graphic is here. You can simply use one of the built-in tools in raster called contour. So you select raster, extraction, contour, and you will get a pop-up window that looks like this. The pop-up window will give you any type of maps that can be used for creating contours, and it looks for raster graphics. Raster graphics are the gridded graphics I referred to earlier. There's only one of them that has elevation data, the one we just created, so we'll use that. And then the interval is where you want to put in your interval for amount of elevation for contours of 1.25 meters. Now, this data was stored in feet. If you remember correctly, when we went to our Puget Sound LiDAR Consortium page and we had downloaded our data, we downloaded all of this raw data. One of the things I also did was save a screenshot of this area right here. And this screenshot tells us what the units were, and the units are in survey feet. So our elevation is in feet. Now, that's going to be important because we need to convert this to meters. We want to do 1.25 meters. So what we do is go to Google and say 1.25 meters is equal to 4.10105 feet. That interval is what we're going to put there. Leave this as it is. Typically all the data is stored with elevation as it's elev as the name that it's looking for. Don't set any offset, just leave it all as it is and press, let me get rid of this, and press run. Now you can store this to memory, or store this actually raw data as you have it, which we will do once it's done, and we'll use that into our contour file folders later on. It's best to keep the raw contours as they are, not manipulated at all, even if it's a little bit junky looking. So now you see we have all the contours. We can now turn off this digital surface model and just look at the contour data themselves. And we can see if it makes any sense by moving the layer underneath the contours. We know that it's lining up pretty well to the shoreline. That makes a lot of sense. We've got the baseball fields here where it's flat. That makes sense. So geographically and geospatially, we know we've got a pretty good set of contours here. What we need to do next is take this contour and save it. Right now it's just in memory, so we can do the exact same thing we did before. We right click on it, export, save features as, and we're going to find the location for these features. Our training map is where we're going to do it. We're going to put it into the EPSG contours working directory, and we're going to say 1.25 meter raw. This we're going to import later on directly into our OpenMapper file as our form lines, as a temporary form line file, I should say. I want to save it as a EPSG 2610. Okay. And you'll see that it will create a brand new file set called 1.25 meter raw. I can now get rid of the one we already have and remove it because it was temporary in memory only. This looks great. It's been re-projected to the correct coordinate reference system. And now we can use this 1.25 meters for all kinds of things. This is going to be handy. So how do we get 2.5 meter or 5 meter contour out of this data? How do we smooth it? How do we make it look better? This lesson is going to be a little bit more computer ease, if you will. So if you're not that comfortable doing some light coding, some light commands, then this might be pretty enlightening for you, and hopefully will help you get over your fear of a few basic commands that we can use built into QGIS in order to control our contours a little bit more. So the first thing I want to do is take the 1.25 meter data, and I'd like to smooth it all out a bit and create a brand new file set that, instead of being 1.25 meter raw, is 1.25 meter smooth. And when I smooth it, there's two things I want to do. I want to get rid of the junk, the little small areas that I probably would never notice, the things that are just slightly above the threshold for the 1.25 meter contour line and then deviate slightly back below. This happens a lot in areas that are very flat, in areas that have a lot of forest clearing. Especially if it's a flat forest clearing or swampy areas, you see a lot of random contours that don't really exist to the naked eye. So I'd like to clean up the small areas like that. And then I'd also like to smooth the contours. So we're going to do that in 2 steps using the exact same plugin in QGIS. And we're going to use this 1.25 meter raw as an input. So hopefully you have already done, as I mentioned in a previous video, gone into the manage and install plugins and turned on the check marks for all of the things in the settings, which will give you experimental plugins. And one of the experimental plugins we're going to use is called the Generalizer 3. That's the one you need to install. Once it's installed, you'll see it in your list of plugins. So what we're going to do is open up the Generalizer and run 2 to 3 basic things, and we're going to iterate this until we get it the way we like it. We're going to use a vertex reduction, remove small objects, and a smoothing. And each of these things might need to be done over and over and over again. And we're just going to save these to memory so that if we don't like it, we can just delete the memory layer and do it again. We're not going to save permanently to our computer anywhere this, just in the memory. So let's take a look at the area. We're going to zoom into a different little area up here around the baseball fields. Okay, this is a nice area because we have a swamp to the right, and you can see all of these little pieces of debris, which the swamp is really just flat pieces of high grass that are sitting around. It's flat. You can never see anything with your eye. We also have, let's say, around this top of this contour line here, you see it's very squiggly looking, and a human being would never be able to see that squiggle. It's unnecessarily complex. This is why drawing the contours is very useful to a orienteer. And then we have a bunch of other small little areas you can see that could stand to be removed. These might be Knowles if you were to see it with your naked eye, but in my opinion, it's better to not draw these things in unless you have to. Because remember, these are 1.25 meter contours, already smaller than you would ever probably notice with your eyes. So smaller deviations from that should probably be not put in unless they're purposefully seen by the field checker. We're going to try to get rid of all that. We're going to try to smooth it all. That's the goal here anyways. Okay, so the first thing I'd like to do is remove, or actually smooth the objects. So we're going to go to the plugin Generalizer, and the first step of smoothing is to remove some of the vertexes. There's so many vertexes in here that you see that we just want to get rid of some of them. For our purposes, I'm going to use an initial threshold of 3 for the vertex reduction. So that's not a whole lot, it's pretty small. You can put in a huge number and you'll see. In fact, let's start with a very big number and we'll see what happens to our contours. We're not going to save it, we're just going to run it, put it in our output, save it as 26910, run it, and you're going to see this is probably not something that we like. It's way oversimplified. It's going to be actually crazy, I'm guessing. Okay, now we can see real clearly that was too much, way too much. So we just want to back out of that. We can right click and delete, remove that layer. Okay, we made a mistake. Let's go ahead and try that again. This time I'm going to use the exact same input layer, 1.25 meter raw. I'm going to use a vertex reduction of 2 instead of 44. Same datum, same coordinate reference system. It's running. Okay, there we go. Now let's take a look at the two and we'll compare them and see how they look. Now, I have to zoom in to kind of tell the difference, but you can already see there's a significant change in the complexity of these lines. We want to definitely keep the complexity to a minimum. I don't really see too much of a problem. Here we are on 1 to 4,000 scale, and that complexity does not seem too much for me. Now remember, we're going to smooth this out even further as well. So that looks good to me. I'm going to keep that right there. I'm going to rename that. Just rename the layer. I'm not actually saving it, just renaming the layer to 1.25 vertex reduction 2. And I'm going to take that new layer and I'm going to run it through another generalizer mode. Next layer I'm going to do is 1.25 vertex reduction 2, the layer up there. I'm going to remove small objects, and I'm going to say I'm going to remove objects smaller than the threshold of 60. Now let's try a different number here too. The same concept can apply. Let's just say 600. Okay, I run that through the generalizer. And now that it's done, we can see what was removed. Pretty big contours and hills were removed. We don't want that. We just want the small stuff. Particularly, we want the stuff that we see in this swampy layer altogether. And let's try it with a more logical setting, which logic comes from experience, of course, but I'm going to give you some numbers here. We're going to select the vertex reduction 2 as the input, and we're going to use 60 as our number. 26,910. Okay, now that looks a lot better. So we can see some of the stuff that was removed. We kept a couple of bigger areas that are inside of the swampy area. We lost a couple of things that might be considered hilltops. So maybe just a little bit more conservative if we wanted to. Clean up some of this stuff manually. Let's remove that. Try it again with a number of 50. Generalizer. Select the correct layer. We're going to go with 50. Now we're honing in on it. Okay, let's change the color of that to something more clear. All right, so now you see what we've lost. Still lost a few things, but not too much. I'm pretty happy with that. Based on my experience, that looks pretty good. We're talking about contours that look like this now. I feel like that's pretty good. If I was to look at my Openstreetmap map as a base layer, I feel pretty good about that as my 1.25 meter base. If I'm still worried about it, I could still go back and delete some more, make it 40 if I wanted to. But for the purposes of this lesson, we're going to leave it at right where it's at with the 50 as the setting for the small object removal. And I'm going to rename this VR2, which is vertex reduction 2, and then small object removal 50. All right, now the third step is to take the exact same data and plug it through a smoothing algorithm. So let's select our layer that has both of these already applied to it. And we're going to go through a smoothing called Boyd's forward-looking algorithm. And there's a lot of random numbers you can put in there, but you want to start small and work your way forward. I'm going to say 3 is what I'm going to use. I'm going to run it. Now we can do a comparison of the two layers together. Okay, so let's zoom in on a few places and see. So now you see that that algorithm smoothed things out a little bit, more pleasant to the eye. And that's a pretty good looking set of contours right there. We could clean up this swamp area if we wanted to, but they look pretty pleasant to the eye. They're clear to see what's going on. All the junk is pretty much removed, and I would feel pretty good about that being my form line base. So now we've got exactly what we want. We're going to save that data. We're going to save it as 26910. We're going to save it in our working directory, and that directory again is in the contours working directory EPSG 26910, and this is going to be 1.25 meters smooth. All right, so we save that, and we can remove this one that's in memory. Remove that layer. So this is our smooth data. This is our raw data. Okay, slightly different. Not a whole lot, but it certainly looks a lot better. Actually, this is the raw data. Definitely looks better than that. Significant reduction in vertexes and items. Now, we've got the smooth data, and what we want to do is create the 2.5 meter regular interval contours, the index contours, the 5 meter regular contour intervals, and the 5 meter index contours. This is where it requires a little bit of understanding and close attention to what I'm doing. So this layer and this layer, the intermediate layers, we can get rid of. And we can actually get rid of the raw layer too if we want to, but we'll leave it there for purposes of conversation. This layer here, if you open up the attribute table, which is this icon that looks like a spreadsheet, it gives you information about the layer. And you see the information is the feature identification and identification, and then the elevation data, which is the actual height of the elevation. But it's in feet, remember. And it's every 4.10104 feet. So it would be handy if that was in meters, first of all. That's what we're going to first do, is change this to meters. Then we're going to put a flag on each one of these contours that tells it if it's 2.5 meter or if it's 2.5 meter index. Do the same thing for a 5 meter and a 5 meter index. So how we're going to do that is we're going to edit this table data. And we do that by selecting the pencil icon. Now it allows us to make changes to this. What we're going to do is we are going to select this abacus icon, which is called the field calculator. The field calculator allows you to create a whole new field. So we have the feature ID, the elevation. We're going to create a new one called meters. And how this works is it lets you select preset items from this middle item here, and then apply it to the scratch pad on the left. And the scratch pad is going to be sort of a computer calculator, if you will. So these are called fields, each one of these. So what we're going to do is we're going to go and select the little arrow next to the fields and values. And it'll show you these three right here. It's very important. This is a very useful feature here, this field and values. So we're going to take the elevation, and if I double click it, you see it brings it over here. And it puts it in the correct format too. It puts parentheses around it. If you don't know what that means in Python programming language, it kind of does this for you. So it puts the elevation over here, and what we're going to do is multiply the elevation by a factor to convert it to meters. So actually we're going to divide by 3.28084 to convert it to meters. And I'm going to look that up in Google just to make sure. Okay, 1 meter is equal to 3.28084. Yep, it's always good to not trust yourself. And then I push the, it has a preview of what the answer might be, but the problem here is that we don't want to just simply press OK. We want to make sure everything is set up right. We want the output to be a real number, not an integer, meaning it has decimals. And then we want the precision to be 2, which would be like 0.25. Be 0.250 if you selected 3. So we have meters as the name of the field. We have a decimal number. We have the output field length of less than 6 or less than, with a precision of 2. Press OK. And now you see we have a new column that has the meters listed there in 1.25 meter increments. So nothing has changed besides we just added a column. Now we're going to use the exact same concept to add other columns. So opening up the field calculator, I'm going to add another column. This column is going to be 2.5 meter contour. Let me make this the way I always make it. Contour. It's 2.5 meter cont. Okay, and this is going to be a integer. It just needs to be 1 digit long. What we're going to do is basically put a 1 next to it if it is a 2.5 meter interval. And how we determine if it's a 1.25 meter interval, or I'm sorry, a 2.5 meter interval, is quite clever. What we do is we do the exact same thing. We open up the fields, and now we have the meters field. We select that, double click it, and there's something in computer language called a modulo, and it's the percent sign. And a modulo is the same thing as looking for the remainder when you do division. So like 8 goes into 24, the remainder would be 0. We're going to do the exact same thing with 2.5 meters. We're going to take the meters, the elevation that's in meters in that column we just created, and we're going to divide it by 2.5. And if the remainder is equal to 0, we see that it'll automatically give you a 1 saying it's true. So it'll flag all of the things that have 2.5 meter intervals as true. And now we see 10 meters has a 1 next to it, 100 meters. We see 121.25 does not. That's good. So it makes sense. And this same concept we are going to apply to the 2.5 meter index. And how we're going to do that is we're going to take the meters again, modulo again. This time, every 2.5 meters, the fifth one would be equal to 12.5 meters. So if it's divisible by 12.5, we'll put a flag of 1 next to it. Okay, now we have a new column called 2.5 meter index. We see that 100 is one of those, and 125, and it all makes sense. We're going to repeat this for the 5 meter interval. And the 5 meter index. Meters, modulo 5. Meters, modulo 25. Now that we have this, we're going to select the pencil again, and it's going to save all of this data. The magic comes when it comes to using this information in order to selectively grab the contours and export them as individual contour types. what we want to do is grab the things that are 2.5 meter contours but not index contours and export them into QGIS, or from QGIS into OpenMapper. We need to save them in order to do that. We need to save the index files for 2.5 meters separately. We need to save the 5 meter contour separately and the 5 meter index separately. So all of these things we're going to save individually and then import them one at a time and associate them with the correct item in OpenMapper. Next step of this is to style the data. So what we're going to do is select the 1.25 meter smooth. Just double click on that. And what we're going to do is select the symbology button. And we're going to use a rule-based symbol. So the first rule that already exists is that if it doesn't have a rule, just show everything. We're going to add another rule. And we're going to say 2.5 meter contour. And we're going to filter for just those things. And we're going to go back. This button is going to take us back to this exact same query builder. So how I did this was in the filter button selected, I selected this little macro icon here. I go to fields and values, and I'm going to say, select the double click on the 2.5 meter contour equal to 1. I'm going to write and capital 2.5 meter index is equal to 0, meaning it's not a 2.5 meter index, but it is a 2.5 meter contour. Okay, so I have that rule. Now let's just apply that and see what this is. So I can see if I turn off all the contours, that's what they all look like. That is just the regular 2.5 meter contour. So now let's do the exact same thing. We're going to build up a rule for every one of these types. 2.5 meter index. We're going to select the query builder, select the fields, select the index is equal to 1. So this will select anything that is a 2.5 meter index 1 next to it. We will select that. Okay. We're going to add another rule. We're going to say 5 meter cont. We're going to go with query builder. We're going to say 5 meter cont, double click, is equal to 1, and 5 meter cont is 5 meter index. So let's erase that. 5 meter index is equal to 0. Okay. And then my last one is my 5 meter index. And I follow the exact same format where I select the 5 meter index is equal to 1. Okay, okay. Now, as we see, I have, let's turn them all off and turn them on one at a time. So I have all contours. I have 2.5 meter contours and 2.5 meter indexes. Or if I wanted to do 5 meter contours and 5 meter index, I have that. Now, of course, I could style this however I want. And these are already smooth and ready to go into OpenMapper. Now it's just a matter of one at a time. We're going to save these. We're going to select this. We're going to zoom out. We're going to use this icon right here, which is the selection tool icon. There's different ways to select, but with that selected, I can highlight everything and it'll turn it yellow. So now I've only selected the 2.5 meter contours. I right click on this contour layer and select export, save selected features as. It's important you select save selected features as. If you say select save features as, you'll select everything that's a 1.5 meter contour. So export, save selected features as, and we're going to label this into our contours directory. 2.5 meter So only selected features is selected. Okay. And it showed up on the screen. We don't need to have this in QGIS anymore. We know we have it saved. So let's remove that. Actually, we'll leave it there for now. We should see the whole stack of the things that we're saving pop up. Okay, now we're going to turn the 2.5 meter indexes on. And what we're going to do is bring this up here so it's easier to see. Unselect everything. And then only have those turned on. Select them. Right click on the actual master layer. Export, save selected features as. Select the directory. 2.5 meter index. Oops. 26910. And make sure it's in the correct CRS. It is. Save selected features. It is. Okay. So these two together should make up the 2.5 meter set. They do. Repeat for the 5 meter set. Right click. Okay, now we should have all of the contours we're going to import. So we're going to import all of this stuff into OpenMapper. There's a lot of reasons to do that, but one thing, it gives you the opportunity to change your contour interval if you want it to go from 2.5 meter to 5 meter, if you've changed your mind, and it's really all done at the same time. The second reason is to give you 1.25 meters to intervals in order to use as either form lines or as to inform the drawer of form lines. So that's the gist of it. We'll get to how to import them into OpenMapper later. But now you know how to create your own contours and how to smooth them in QGIS. Any variation of this is obviously fine, and it's best to play around with things until you get them just the way you want. That's the end of lesson 4. Hope you got something out of it. If you have any questions, contact me at Tahoma Orienteering at gmail.com.